In this video, we're computing the integral from -1 to 1 of x to the fourth minus x cubed plus x dx. Now, of course, we can handle this integral by using brute force. In other words, just integrating all three of these terms, applying the limits of integration, and simplifying the result. So I'm going to go ahead and start with that, but there's a way better way to do it by exploiting the symmetry of these functions. So I'm going to illustrate how you can use those symmetry ideas to cut out about 3/4 of the work on this problem. So first, the brute force method. I guess the antiderivative here, which is going to be 1/5 x to the fifth. This is just the power rule backwards. And 1/4 x to the fourth. And a 1/2 x squared. And I said that a little weird. There's a minus sign on the x to the fourth term. Now we're evaluating this from -1 to 1. When we plug in that upper limit, we replace x with 1, and we just get 1/5 minus a fourth plus a half. And you might be tempted to get a common denominator and add all those together, but it's not necessary, as we'll see in a minute. So when I sub in my lower limit, -1 to the fifth power is -1. So my first fraction becomes a -1/5, but the other two are unaffected because even powers of -1 just give me 1. So I end up with a -1/4 and a +1/2. And so what I notice here is I get a really nice cancellation. When I distribute this minus sign through the parentheses, I end up with a +1/4 that cancels the -1/4 in the first term, and I end up with a -1/2 that cancels the +1/2 in the first term. And this is no coincidence. If you're aware of the symmetry of our original functions, you can see this coming. So I also end up with a +1/5 in that second term, and I combine it with the one out in front, and I end up with 2/5 for my final answer. Okay, so what about the symmetry approach? What I notice in this integrand is I have an even function here. X to the fourth has even symmetry. And then I have two odd functions. X cubed and x are both odd functions. Now, if this idea of even and odd functions is new for you, I'll post a card at the top of the screen to my basic introduction video on even and odd functions. And so when we have an integration interval that's symmetric about the origin, so that's the case here, I'm going from -1 to 1, which happens, by the way, in a lot of real applications, I'm looking to exploit the even and odd properties of these functions. The integral of an odd function on a symmetric interval like this vanishes. So I know this integral breaks up into 3 integrals, but 2 of those are integrals of odd functions that vanish. And so basically I get to ignore those 2 pieces of the integrand. And so that moment where I cross out those odd terms, that actually corresponds to this same cancellation that we did when we applied our limits of integration in the brute force method. Now there's one more thing I want to do here. Because x to the fourth is an even function, I'm allowed to just cut the integration interval in half. So I'm just going to go from 0 to 1 and then double the result. So I put a 2 out in front. And the advantage there is that if I have a 0 for one of my limits, it simplifies the math tremendously. Now all I have to do is guess the antiderivative of x to the fourth, which is 1/5 x to the fifth. And then we evaluate from 0 to 1. And we like our 0 because when I sub in that lower limit, I just get 0 out of it. So we don't even have to worry about it. And then when we put in our upper limit, replace x with 1, and we arrive at the same answer, 2/5. So when I'm grading papers, I would consider that second solution to be far superior. I would probably throw in some bonus points for that. And the reason I care about this so much is that the idea of exploiting the symmetries of a problem really is a critical skill for applied mathematics, physics, and engineering. So I encourage you, the next time you see an integration interval that's symmetric about the origin, see how much you can cut out of the problem by using even and odd functions. If you think you've gone too far out on a limb with the symmetry argument, you can always check your answer with the brute force method, but it will pay off to make a regular practice of looking for these things. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.